Hello, and welcome back to part two of the video lecture on the four-step hypothesis testing and the logic of hypothesis testing as well. So at this point, we have covered step one and step two, and we are now at step three, which is the math. Here is the Z hypothesis test formula, where the numerator is the differences between the means and the denominator is always the error term. The error term in the Z test statistic is called the standard error, and it can be calculated by dividing the population standard deviation by the square root of the sample size. So all the math that you will need in order to calculate your step three of the hypothesis test will always be found in the scenario. And so you can see that the sample mean is 30, the population mean is 26, the standard deviation is 4, and our sample size n is 16. There's one sample but 16 babies in the sample. So if we divide the standard deviation of 4 by the square root of 16, we would get a standard error of 1, as you see calculated here. So with the standard error of 1, we've taken care of the denominator of the Z hypothesis test, and now we can put in the sample mean of 30 minus the population mean of 26, which would give us 4, divide that by the standard error, and we would wind up with a mathematical outcome of 4. Our Z test statistic has a mathematical outcome of 4. And now the question becomes, is this Z test statistic, is this, again, test statistic, a high probability outcome or a low probability outcome? And once we've answered that question, do we have a high or a low probability outcome? And remember that we're talking about high or low probabilities that HO, our null hypothesis, is true. So another way of saying that would be, do we have a high outcome, a high probability outcome that there is no effect, that HO is true? Or do we have a low probability outcome that there is no effect, that HO is true? Once we answer that question, then we can make one of two decisions. There are only two possible decisions that you can make. You can either reject the null hypothesis or fail to reject the null hypothesis. But again, before we make one of these two possible decisions, we have to first answer this question: do we have a high or low probability outcome? And to answer that question, we have to actually go back to step two, to when we set the critical regions and we divided our distribution of sample means into areas of low probability, which we called critical regions, and areas of high probability. And so our test statistic was equal to 4. 4 lies to the right of this critical region line, right? Z is 1.96. That's our cutoff critical value, 1.96. And the 4 would fall into this critical region, into the tail of this distribution. Our mathematical outcome is a low probability outcome, and it is in the low probability area that we call critical region. So that if the test statistic, the mathematical outcome, the 4, If the test statistic falls inside the critical region, and it does, because remember the critical region is the tail, so the 4 does fall inside this critical region, then the probability that the null hypothesis HO is true is very low. In other words, the probability that there is no effect is very low. It's critically low. As a matter of fact, the probability that HO is true is so low that we reject HO and conclude that there was an effect. If the test statistic had fallen outside the critical region, meaning it would fall outside of the low probability areas and instead fall in this high probability area, then the probability that HO is true, the probability that there is no effect, is very high, and therefore we would fail to reject the null hypothesis and conclude that there was no effect. That's a difficult concept to get, but I think with practice, most of you, if not all of you, really aren't going to have much of a problem with it at all. Once we make our decision, then we have to interpret the decision and write up the results. So again, going back to our mathematical outcome of a z-test statistic equals to 4, remember it did fall inside the critical region. It was a low probability outcome. Therefore, the correct decision is to reject HO. When we make this decision to reject HO, then the interpretation is that yes, there is an effect. And we'd have to write up that interpretation. And so one way to write it would be simply to state our study supports that touch did have an effect on weight. The data were significant. And then we would have to write up that result in a statistical way, in a statistical statement, if you will. And statistical statements always begin with the letter of the test followed by the mathematical outcome of the test. In our case, we ran a z-test, so we would use the letter z equals, our mathematical outcome was 4, followed by a comma, and then we would write the decision that we made, but we would write that decision in probability format. So remember that our mathematical outcome was a 4. The 4 fell in this low probability area, this critical region area, so that this mathematical outcome is a low probability, causing us to reject the null hypothesis. So in writing up our statistical statement, we would write z equals 4, probability less than 0.05, to indicate that this outcome is a probability that is less than our alpha, therefore a low probability, a critical region probability, and that we had rejected the null hypothesis. If you had done the 4 steps described so far between part 1 of the video and part 2, this video, your 4 steps would look like this. What I have represented here is the original research scenario that we began with, where, remember, a researcher hypothesizes that providing lots of touch to premature babies will have an effect on their weight. You may remember then that this would be a non-directional hypothesis requiring us to use a two-tail test. So again, if you had this research scenario and you were going to go ahead and carry out the 4 steps, your step 1 would look like this. You would write HO for the null hypothesis, H1 for the researcher's hypothesis, sometimes called the alternative hypothesis, the scientific hypothesis, and so H1 would be touch will have an effect on weight, and HO, the null hypothesis, would be that touch will not have an effect on weight. Step 2, you would set your critical region, because this would be a z-test at an alpha level of 0.05. As described in the previous video, we would wind up with these critical values of negative 1.96 and 1.96, and this is the critical region, this is the critical region, and then in step 3, you would go ahead and do the math. In this particular scenario that I have used for the demonstration, we would wind up with a test statistic equals to 4. And then we'd have to ask ourselves, is this a high probability outcome or a low probability outcome? Well, the 4 would fall somewhere out here in this tail, so it is a very low probability outcome. And if our test statistic falls inside that low probability outcome area, that critical region area, then the right decision would be to reject the null hypothesis. And the interpretation would be that touch did have an effect. We would write that up as our study supports that touch did have an effect on weight. The data were significant, followed by the statistical statement. If we had had a different result, imagine that when we did the math in step 3, instead of a value of 4, we got a value of 1.5 instead. Notice that in this case, the 1.5 would fall here. It does not fall out in the critical regions, but rather it falls in this high probability area. When the test statistic falls in the high probability area, probabilities higher than the alpha, then the correct decision is to fail to reject HO. We wouldn't reject it. In other words, we'd hold on to it. And HO, remember, is the null hypothesis that states there is no effect. Therefore, by failing to reject it, the interpretation would be that our study supports that touch did not have an effect on weight. The data were not significant. And notice then that in the statistical statement here, we'd still put in the letter of the test, we'd put in its mathematical outcome, but notice here that the probability of this outcome is a probability higher than alpha. It's a high probability outcome. Again, because it did not fall. This test statistic result of 1.5 did not fall in the low probability area, but rather in this high probability area. Now, imagine that we were working with a directional test. Again, we discussed directional and non-directional in part 1 of this video lecture series, but I just thought it might be not too bad an idea to say a little bit more here. If the research scenario had a hypothesis that clearly indicated a particular direction, such as this one, that touch to premature babies will increase weight, then your 4 steps would look like this. In step one, the researcher's hypothesis would be a positive one, right? Researcher's hypothesis or hypotheses are always positive. They will always say that something will happen. So the researcher's hypothesis is that touch will increase weight. The null hypothesis, the one we actually test when we run a hypothesis test, would be the nullification of the researchers. And so the null hypothesis would state that touch will not increase weight. In step two, when you're setting the critical region, now running a z-test with an alpha level of 0.05, because we are expecting an increase in weight, we're expecting an effect to the right of the mean. We would only be looking for an effect in one tail. So the z-score that cuts off that 5% of the distribution is 1.65. If we did the math, we would get a z mathematical outcome of 4, and notice that the 4 does fall inside the critical region. The 4 is a low probability outcome, so that we would reject the null hypothesis and conclude that our study supports that touch did increase weight. The data were significant, and z equals 4. Again, the 4 is a low probability outcome, a probability less than our alpha, and so we would write probability less than our alpha to indicate that this is a statistically significant outcome, that the probability that there was no effect was lower than alpha, and therefore we rejected the null hypothesis and conclude that touch did have an effect on weight, or in this case, touch did increase weight. If the direction had been, or rather if the hypothesis had been in the opposite direction, if the researcher hypothesized that touch to babies would decrease weight, now we would be looking for an effect to the left of the mean, right? We would be looking for an effect on this tail of the distribution. So that the researcher's hypothesis now would read touch will decrease weight. The null hypothesis would state that touch will not decrease weight. But now in step two, when we set the critical region, we're going to set it on the left-hand side because we're expecting a decrease in weight. And so we would still partition out the lowest 5% of the distribution, because remember, we're always going to work with an alpha level of 0.05, and now would be a negative z-score to partition out the bottom 5% of the distribution. In step three, when we did the math, we would still wind up with an outcome of 4, but notice now that the 4 is an extreme value, but it's in this right-hand side of the distribution, and we are not looking for an effect here. We're looking only for an effect on this side. So in this case, despite the 4 being way out here in this tail, it doesn't matter because we did not set any critical region in this tail. We only set it in this tail. We are only looking for an effect on this side of the distribution, so that our mathematical outcome of 4 is not a low probability outcome, meaning that it did not land in our low probability critical region that we set. Therefore, we would fail to reject HO, and conclude that our study supports that touch did not decrease weight. The data were not significant. So again, the letter of our test, its mathematical outcome, and then the probability of that outcome. And this was a high probability outcome. Type 1 and type 2 error. Anytime that you run a hypothesis test and then you make a decision in step 4, whether you reject the null hypothesis or fail to reject the null hypothesis, no matter which decision you make, there is always going to be a probability that you are wrong. Remember that hypothesis tests are based on probability and not certainty. So when we make our decision to either reject the null hypothesis and say, yep, there is an effect, or fail to reject the null hypothesis and say, nope, there isn't an effect, either way, we can always be wrong. Because again, our decisions are based on probability and not certainty. So when you make the decision to reject the null hypothesis, you always have the probability of making what is called type 1 error. In other words, if your decision is to reject the null hypothesis, you can always be wrong. And what that means is that you rejected the null hypothesis, you concluded that there was an effect, but there really was no effect. If you make the decision to fail to reject the null hypothesis, you can also be wrong, and we call that type 2 error. Type 2 error happens when you fail to reject the null hypothesis and you conclude that there was no effect, but there really was an effect. Your hypothesis test just missed it. Again, this can be a little confusing, but what you want to remember is that it doesn't matter whether you reject the null hypothesis or fail to reject the null hypothesis. Whichever of those two decisions you make at the end or in step 4 of your hypothesis test, the thing that's important to know is that there is a probability that either one of those decisions are wrong. And type 1 error is the name of the probability by which you can be wrong when your decision is to reject the null. So any time that you reject the null hypothesis and you conclude that there was an effect, you could be wrong. And type 1 error is the probability that you're wrong. And the probability that you could be wrong of type 1 error is always equal to your alpha level. So if your alpha level is 0.05 and you reject the null hypothesis, there is a 5% probability of type 1 error. If your alpha level were 0.01 and you rejected the null hypothesis, there would be a 1% chance of type 1 error, or type 1 error would be equal to 1. Conversely, if you make the other decision, failing to reject HO, again, you make the decision to fail to reject HO, and you conclude that there was no effect, you could also be wrong, and that would be type 2 error. You're saying that there is no effect, but the fact is that there was an effect, and you just missed it. Lastly, Anytime that you do reject HO, then you have what's referred to as significant results, and you can conclude that indeed you do have an effect. And if you wind up being able to conclude that you have an effect, then you can measure the size of that effect. And so effect size, the statistical symbol is the lowercase d, and you can calculate the size of your effect by calculating Cohen's d, which can be done by subtracting the sample mean from the population mean and dividing by the standard deviation. Once you calculated Cohen's d, if you got a d value of around 0.2, that would be a small effect. If you got a d value of around 0.5, that would be a medium effect. And if you got a point d value of around 0.8, that would be a large effect. I know that the logic of hypothesis testing and this four-step process, it can be daunting at first, but I promise you that if you read the text lecture very, very carefully, and then you listen to part one of this video slowly, stop it at some points, take some notes, listen to the second half of the video, and then engage in doing some practice problems, I promise you that it will not be long before these four steps seem a lot less complicated than they do now. Talk to you soon.